Syntax builds the form we see. Semantics gives it meanings key. Connectives link what minds devise. Quantifiers range through truth and lies. Modus ponens strikes with might. Modus ponens flips the fight. Logic cuts clean, no shallow line. Through the long night, reason shines.
Previously, we discussed quantified statements with only one variable and their rules of inference. To express more delicate ideas and explore more complex structures, we often need to make statements that involve multiple quantifiers. In this section, we focus on two quantifiers applied to formulas generated by binary predicates. Most of the discussion here can be easily generalized to predicates involving more variables and more quantifiers. To this end, let D be a domain of discourse and P a binary predicate, which, when applied to variables x and y, results in the formula Pxy. The variables x and y are called free variables. As we have seen before, there are two ways to eliminate free variables. The first way is to replace a free variable with a constant. The second way is to bound the free variable with a quantifier. A formula without any free variables is called a closed formula, for which we can evaluate its truth value. Consider the following formulas. For example, this is not closed, both x and y are free. This is not closed, x is replaced by the constant c1, but y remains free. This is closed, both variables are replaced by constants c1 and c2, respectively. This is not closed. X is bound by a universal quantifier, but y is still free. This is closed. X is bound by a universal quantifier, and y is replaced by a constant c2. This is closed. Y is bound by an existential quantifier, so the inner formula becomes a statement about x, which is in turn bound by the universal quantifier. To see a more concrete example, let D be real numbers, Pxy be the formula that x is greater than y. Then, each of the following formulas is closed. From now on, we focus on statements involving two quantifiers. By a slight abuse of notation, we may write them with optional parentheses and punctuation. When ambiguity arises, we will use parentheses to indicate the precedence between quantifiers and logical connectives. Our first task is to discuss the negation of such statements. The three steps we introduced earlier remain valid. The domain or subdomain remains unchanged, the quantifiers are flipped, and the formula is negated. The only added complexity is that we must be more careful in identifying the scope of each operator. Let us work on some examples. For all x in A, there exists y in B, such that if Pxy, then Qxy. Here, a conditional compound formula is bound by an existential quantifier, which is then bound by a universal quantifier. To negate it, first flip the quantifiers, then negate the conditional. The negation reads, there exists x in A, such that for all y in B, Pxy and not Qxy. Another example. Recall that a real-valued function f from A to R is bounded from below if there exists a real number that serves as its lower bound. Formally, this means there exists y in R such that for all x in A, fx is greater than or equal to y. Now consider the function f from R to R, defined by fx equals 2x. To show it is not bounded from below, we negate the definition. For all y in R, there exists x in R such that f of x is less than y. To prove this, let y be any real number. Pick x to be 1/2 of y minus 1. Then f of x equals y minus 1, which is less than y. So we are done. Finally, consider the function fx given by 1 over x defined on R+. We claim that the function does not possess any minimum. Recall that saying the function has a minimum means there exists a real number y such that y bounds the function value from below and y is achieved. As a result, we should prove its negation. The rough idea can be easily explained by the graph. If y is non-positive, then y cannot be achieved. Yet if y is positive, then y cannot bound all function values from below. To write proof rigorously, let y be an arbitrary real number. If y is less than or equal to 0, then for any x in R plus, fx is equal to x inverse, which is strictly positive, thus is not equal to y, and hence the second part of the disjunction is true. Otherwise y is positive, then take x to be 2 over y, which is in R plus. Moreover, fx equals to y over 2, which is strictly less than y, hence the first part of the disjunction is true. We conclude that no real number y can be the minimum of the function f. The correct negation of a statement involving quantifiers, especially when mixed with logical connectives, can be technical, but it is essential. Negation is often the first step towards strategies such as proof by contrapositive and proof by contradiction. We hope this section has provided a basic understanding of how to obtain and work with such negations. In the next section, we will explore the order of quantifiers and the subtle differences it introduces.